All right. Well, we're going to start a new chapter, and this chapter is on electrons, which may seem a little surprising to you because we just had a whole chapter on atoms. Electrons were just one part of an atom. We talked about protons, neutrons, and all that other stuff. Avogadro's number, moles, atomic masses, ions, isotopes. And now I'm going to spend an entire chapter just talking about electrons. Okay, why is that? Well, there's a couple of reasons. One, electrons are the most important thing when it comes to chemistry. They're way more important than all the other ones you're going to talk about. Protons, the other parts, subatomic particles, nothing compared to electrons. Almost every chemical reaction that you're going to do is going to involve electrons, not protons, not neutrons. Those are nuclear reactions. Okay, electrons. So that's the number one reason. But here's another reason. As you're going to find out today in the next 3 days, electrons are weird. They are not what you think they are. Electrons are very strange guys. We have this vision of electrons, of this kind of atom like that. You know, like that's our atom. We see that. That's actually a symbol for nuclear power. We envision these electrons going around the nucleus like the Earth goes around the sun, or like the moon goes around the Earth. And it's not at all what electrons are. And they say, well, why do they draw it like that? Well, there are some things that are right about it. As the Earth goes around the sun, it spins. All right. But that's, you know, there's other things. It is actually going around it in some way, shape, or form, but not in these nice, simple orbits. All right. So we see another vision of the atom, model of the atom you've probably used over the course of the your tenure in science classes, middle school, high school biology. You probably saw this version, I should say. And I see actually the same picture that was above one of the worksheets I gave you. Okay. And this seems to show these rings. Well, it's trying to illustrate something else here, that they're not really rings, they're energy levels, and there's like the shaded area is trying to show you it has 3 dimensions. It's like a ball rather than a ring, a circle. And it's got energy levels where electrons can exist. And that's got some things that are correct about it as well, but mostly it's wrong also. Mostly it's very wrong. Electrons are weird guys. They don't just go around the nucleus in rings. They're not little circles, little specks of dust traveling around the nucleus in rings. They are really strange guys, and I'm going to show you exactly how strange they are, all right, as I go through the day today. All right, I think you're going to realize it.
We're not just going to get back to us.
I have them graded, but we have a single today, so probably tomorrow. They're probably online. They're on Edline, I bet you. You can look them up if you wanted to. All right. So, okay, so there you have it. This is your models that you've seen of an atom, not very good. I'm going to try to describe electrons using something called the quantum theory. All right, this is all part of Chapter 9 on electron structure. All right, and I'm going to use something called the quantum theory. The quantum theory, as the word kind of implies, is going to be kind of difficult. Okay, quantum mechanics, quantum physics. Okay, do you really understand it? Will you really understand it when I'm done talking to you today? Absolutely not. Now we've seen this before, where in the last chapter I was talking about where to get average atomic mass from, and how it's related to moles, and how it's related to Avogadro's number. Tried to explain a little bit to you. I think if you tried, you could understand that. Most of you, it's not beyond your capacity. This is. It's beyond my capacity to envision this stuff. It seriously is. There are a handful of professors at universities that do research that might really understand quantum theory. All right, at any given at major universities. Most people don't, because it's very hard to envision this. As a matter of fact, no one can see an electron. No one. I don't care what university you're working at. You can't see an electron. Okay, it's not something you could see and touch, but there are a lot of things we can do experiment-wise that we're going to see the results of. Matter of fact, in this chapter, which is kind of weird, we're going to be talking about electrons, which are so weird, and yet we're going to have 2 labs we're going to do on them, including a demo today, a lab tomorrow that's going to start, and then a second half of the lab on Wednesday. all right, where we're going to be working with electrons. We're going to be exciting them. We're going to be having them jump around for us and move to different energy levels. We're going to see the results of that. But that's different from actually seeing an electron. Okay, no one can see an electron. So you could probably think to yourself, well, how do they know any of this stuff? Well, most of it's mathematical models that tell us these things and whether they fit these models. They're beyond me. They're beyond you for sure. All right, I know you're thinking to yourself, well, if I just had no, it's not like that. It's not like if I just read the dictionary, I'd know every word. It's not like that. It's very, very confusing. And you'll see that with just my first two postulates of the quantum theory. There are three I'm going to give you, but the first two are going to illustrate this point very, very well. How it's not just a matter of, well, I'm smart. You tell me it, I'll write it down, and I'll know it. It's not like that. Watch. First statement seems easy enough. It says that electrons can only exist in definite energy levels, in certain specific energy levels. Because of the equations they use, because of the quantum theory says that you can only have electrons existing in particularly defined energy states. That seems like, okay, so what's so hard about that? And you're right, there's nothing hard about that. I can envision that. The way we represent that in these models is by those rings or energy levels. Okay, let's go back to that. The rings, these rings. There's an electron right there. He's in that first energy level. Here's a second energy level. It's further away. Third energy level, fourth energy level. I mean, yeah, they're not really rings. They're really in 3 dimensions. It's like a basketball rather than a circle. But okay, I can envision that. It's not that hard. All right. Now, let's get the second statement of the quantum theory. The second one says, and this is the crazy part about the second one, it inherently contradicts the first one. The second one says, electrons can change energy states by absorbing or emitting specific amounts of electromagnetic radiation. And there seems, believe it or not, you don't see it right away, but if you think about it, there's an inherent contradiction in these two statements. And I'll explain what I mean by that in a second. It turns out this is the best we've got, the quantum theory, and explaining this is kind of hard. Does anybody really understand it? I don't know, honestly. There are people who will tell you they do. They're mostly quantum physicists and chemists who will say they understand it. But let me explain to you how weird it is after you write this down, because it is weird. Electrons are not just little moons orbiting the Earth. Not a little solar system down there. It's similar in some ways, but very different in others. Let me show you. Let me go back to this one again. Let me show you how these two statements are basically inherently opposed to each other. Turn that light off. See it a little bit better. Okay? Watch. The first statement says, very simply, electrons can exist at energy levels. So there's one. I'll draw one there. Here, I'll draw one in the second energy level. Here's one in the fourth energy level. Okay, I can envision that. I can also envision the second statement saying, these electrons can jump. They can get energy from electromagnetic radiation. They can jump up to a higher energy level. Okay? Now, here's the problem. How'd they get there? How'd they get from here to here? If I want to go from Berwick to Wilkes-Barre, I got to get in my car or walk or drive or whatever, ride my bike, up Route 11 or Route 81, and I got to go through every point in between, every town in between, every point in between. Not these guys. They're here, and now they're here. They absorb this piece of it, this packet of energy, and now they're up there. How do they do that? I don't know. Okay? Can particles do that? Could just move through space and change everything about themselves without going through every point in between? No, they can't. So, in a sense, electrons, believe it or not, they have mass. So they're kind of like particles. But electrons are kind of like waves. Waves can do this. Waves can change energy levels. They can change. You can change the amount of energy, or even think of a simple wave like a sound wave. So you guys have all, if you don't play an instrument, you certainly listen to music and you sang. I don't have to hit every note on the octave when I'm going up from low C to high C. I don't have to do that. I could hit one, and then I could sing a higher note, and then I could sing a lower note, and I don't have to hit everything in between. Waves are like that. Waves can do that. Particles can't. I want to get from here to Wilkes-Barre, I got to go through every point in between. Electrons, they're kind of like particles. They're kind of like waves. They're very strange guys. They're moving at the speed of light. They have that kind of energy to them. They're moving so fast. They're such light particles, but they do have mass. They're moving near the speed of light. How can all these things, how do you reconcile all this stuff? Well, really, like I said, 99% of the theory is mathematical, and it's way beyond me. So it's certainly beyond you. But this is just my job over the next 3 days is to show you how your vision of the atom is not what you think it is. It is not a very good one. It is not this is the Earth, and this is the sun, and the Earth's spinning around, and it's going in the same little orbit all the time. Maybe it wobbles a little bit, but that's about it. No. Electrons are flying around the nucleus. At any given time, you don't know where he is. He could be here, then he's over here, and he doesn't have to go in between. It's so strange. It's so weird. How do you envision that? I don't think you do. I don't think you ever will. But there are some things, I don't think I ever will, honestly. But there are some corollaries to that. There are some things we can study about this anyway. All right? So let's talk about that. How do we make these guys change their, put the light back on for me, we'll take some more notes here. It says here I can make them change their energy levels by giving them electromagnetic radiation. What is that? Let's talk about that, how we do it, and I'm going to do a little demonstration for you of it today. We're going to do a much bigger one tomorrow. It's going to be more of a lab, and we're going to do a much bigger lab than that on Wednesday. Okay? And all three of them are going to be different ways we're going to give electromagnetic radiation, energy, to the electrons and see what they do. So even though I can't see an electron, I can see the results of what they do when they change. By the way, we all know this. We all know this because we all use electricity all the time. And what is electricity? It's just a flow of electrons. Every time you turn on a TV, power up your phone, it's electrons that are doing these things. So even though we may not understand them, we don't understand what they are, we certainly know how to use them. Okay? We certainly know how to use them. All right, let's talk about electromagnetic radiation. How am I going to excite these electrons to see what they do? How am I going to give them energy? Well, I'm going to give them energy by electromagnetic radiation, which is a very weird thing in and of itself. You probably didn't know this, but you're very familiar with many forms of electromagnetic radiation. In general, it is just a form of energy that exhibits wave-like behavior as it travels through space in photons, that are called photons. Now, it doesn't mean very much to you, but I can show you a couple of pictures up here in a minute. It will. You'll be very familiar with a couple of forms, not just a couple, many forms of electromagnetic radiation. You are right now being bombarded by electromagnetic radiation. Bombarded. Are you worried? Well, you should be sometimes, and other times you shouldn't. All right? It really depends a lot on which particular type of electromagnetic radiation you're being. And I'll use EM radiation, EM, electromagnetic radiation, to abbreviate that, just to make it a little bit easier to say. Well, that's the definition, but let me tell you a little bit more beyond that, what it is, what this stuff is. And you're going to be busy today because you're going to be turning those lights on and off. We're going to need to turn the lights off in a second. Okay, let's take a look at some examples of electromagnetic radiation and what it really is. Okay, turn that light off. Okay. Right now, all these forms of electromagnetic radiation are reaching the Earth, and they're in this room right here, pretty much, most of them. Okay. We have gamma rays, X-rays, ultraviolet rays, all coming, not a lot, but there's some in this room right now. We have visible light. Visible light is a form of electromagnetic radiation. It's different from X-rays in one thing and one thing only, how far apart the waves are. But they're the same thing. So is infrared, so are radio waves, so are microwaves. The only difference, if you notice, is how far apart the waves are. That's it. The only difference between, believe it or not, let's break it down even more. Let's go back to the other one. Let's break it down even more. The only difference between red light and purple light is the wavelength. That's it. Red light has a slightly longer wavelength than purple light. And both of those wavelengths are very small, somewhere around the pin of, around a bacterium looks like. Okay, very, very small, around a single cell. Very, very small. You get even smaller, 10 to the negative 12th. This is like 10 to the negative 6th, 7th, 5th, whatever. You get around negative 16th, negative 18th. You got X-rays, gamma radiation coming from the sun. Stuff that turned the whole green. Bad stuff. Down on this end, we got very large wavelength, 10 to the second, not negative, second. Stuff as big as a person, or as big as a building, or as big as a mountain. Those with really long waves, like radio waves and microwaves are in there somewhere, right around here. Microwaves. They're going through your body right now. How do I know there are radio waves in this room? What can I do to prove it? Turn on a radio, and I'll get a station. Okay? Driving in your car. Radio waves are going through you right now. They're going through you in your car. They're going through you all the time. Are we worried about that? No. And here's the reason why. It all has to do with the wavelength. Okay? Remember Bill Nye asked you to watch that Bill Nye. I would not have shown that ahead of this, but I was gone on the field trip, so I had to. I would have shown it after this class when I was talking about. Oops, sorry. When I was talking about after I've already done this class. He showed you this. He talked about the three things you wanted to talk about with waves, and one of them was wavelength. Remember, it's just a distance between two equal or two same points on a wave. So two peaks or two troughs, whatever. That's the wavelength. Okay, and notice over here you have very small wavelengths. And again, this is not representative. The actual size of the wavelength of an X-ray is around the size of an atom. That's how far apart the waves are. Okay, now they're all traveling approximately the same speed. So what's changing is the wavelength, and a lot more of those waves are going through you if you have a very small wavelength, all right, and a lot less if you have a very big one. Okay, so we're not really worried about things like radio waves and microwaves. All right, they are the size of people or football fields or mountains or buildings. But very small ones we are worried about, and I'm going to tell you why we're worried about, because there's a relationship between the wavelength and the energy. There's a very obvious relationship. Well, who could tell me what that relationship probably is going to be? The longer the wavelength, what happens to the amount of energy these things have? Greater or smaller? Less. Way less energy for these guys. Way more energy for those guys. Okay. Let's see that with an actual equation, which we'll be using and doing problems with in a few minutes. Okay? Put that light back on. All right. So that's what electromagnetic radiation is. Before I actually get to the calculations, I guess I want to do my demo. I almost forgot. Let me show you what I want to do for my demonstration. Yeah. If you have to. All right. You're going to miss my demo. It's pretty cool. You're going to miss it.
Yeah, I'll go online and watch. Can I do that?
Online. Yeah, you can watch it online. It won't show up as well. All right. Okay, you ready? Turn that light off again. I poured out some tonic water in one of these and some seltzer water in another one. Now, if you know what tonic water is, anybody ever taste tonic water? Anybody ever have a gin and tonic? Your parents like gin and tonics? You ever taste one? Tastes like Christmas tree needles. That's the gin part. But tonic water is not the greatest thing in the world. It's pretty bitter. And it tastes bitter because of a chemical called quinine. Seltzer water is just basically water with bubbles in it. Both of these would have bubbles in it, but I've already poured them out, so there's no bubbles left. Okay? So you're watching this, right, Ben? I know you're up all night doing the lab late, but you can still watch this. Okay. Let me show you something about this. I think I kind of need to go back to a dark screen. I want to go back to a dark one so you can see it better. Okay? You ready? Now, this is a black light. Okay? It's a black light. You guys know what happens with a black light. Around Halloween, you use these all the time, right? People, if you have fluorescent paint, you put it on things, it makes it glow, right? Okay. Watch what happens when I give the ultraviolet. It's basically ultraviolet light. That's what a black light gives off. I put these next to these two. Can you see it? See the difference between them? Look at that. Okay. It's pretty obvious. With the ultraviolet light on it, this one glows. All right, that one glows. This one doesn't. It all has to do with a chemical called quinine and his electrons. I'm exciting his electrons. I'm making them jump. Leave that light off. I'm making those electrons jump to a higher energy level. Now, like any other thing, when it goes up to a higher energy level, it can't stay there. Okay, I throw this pin up in the air, even though it's dark, I caught it because it fell back down. It can't stay there. When this guy falls back down, he gives off a same amount of energy he absorbed. Now remember, because they only exist in certain energy levels, they absorb and release this energy in packets of information, packets of energy called photons. And you can see that packet of energy that's given off. You can see it as a specific color, like you just saw, that blue glow, that color. It's given off that particular, this one happens to be these electrons happen to be sensitive, this atom happens to be sensitive to ultraviolet light. And the electrons get excited, they move up to higher energy levels. When they fall back down, they give off energy in the form of electromagnetic radiation, which, remember, visible light is. Now, not always are these things given off in the visible spectrum, but a lot of times they are. For example, tomorrow, I just excited these electrons by using ultraviolet light. I can excite electrons using other forms of electromagnetic radiation. Tomorrow, we're going to use electricity. We're going to pass it through a gaseous phase of this, actually with most of the air sucked out of it in a vacuum tube, just a little bit of any one of a number of chemicals we're going to put in there, elements, and you're going to see a specific color that's going to be given off. And guess what? There'll be different colors for different atoms. They'll be as different as fingerprints. Because when these electrons get excited, every one of those guys up there on the periodic table has a different number and arrangement of electrons. So when I excite this guy's electrons, I'm going to see red or green or blue, depending on what guy I'm talking about. Tomorrow, we're going to excite electrons by passing electricity through them. All right? Today it was just a little demonstration. Tomorrow, you're going to be able to identify them. You're going to see them, you're going to draw them, you're going to color them. I have little spectrums. You're going to look through a spectroscope and see what they look like. All right? You're going to see what happens. Okay? All right. Now, let's get back to my notes here. Oh, I don't want to go that far. Let's just skip ahead here. All right. Now, turn that light back on. Now, as I was saying here, the energy that these atoms absorb or release is related to, matter of fact, in any energy, electromagnetic radiation, is related to its wavelength by being inversely related. As one guy gets bigger, the other guy gets smaller. So wavelength gets longer, the energy is less. And vice versa. As I have smaller wavelengths, I have more energy. Okay? It's an inverse proportionality. It's an inverse relationship. The wavelength of light absorbed or released is inversely related to the energy change by this equation right here. And that's an equation we're going to be using. Delta E equals hc over lambda. And don't worry, I'm going to give you what each of those things mean. Let me move these out of the way. Delta E equals hc over lambda. Now, first off, I want to explain to you mathematically why this works. Okay? Lambda means wavelength. That's the wavelength. And delta E is the energy. Okay? Energy and wavelength are right here. Okay? Matter of fact, before I even explain the reasoning behind it, let me just do this. Let me just give you the actual definitions of each of the terms. I think I should probably do that first. Delta E. You know what delta means in a math problem, right? What does delta always mean? Change. So delta E will be the energy change. The energy change of the electrons, what is the absorbing or releasing at this case? And that's what delta E is. That's what I'm solving for in some of these problems. H and C are constants. You do not need to memorize them. You need to write them down right now so you have them in your notes. But you don't need to memorize these. I will give these to you on the test. See, I have them written over there on that board? They'll stay up there. H is called Planck's constant, and it is 6.63 times 10 to the negative 34th joule seconds. 6.63 times 10 to the negative 34th joule seconds.
We need to know Planck's.
I just said what? Do you need to memorize Planck's constant? Everybody who heard me say that. I'm going to rewind the video and show you. Do we need to memorize Planck's constant? It is shocking. It is shocking. People are looking at me. For those of you at home watching this, people are looking at me wondering what the correct answer is at this point. They need to rewind the video. What did I just say? No. I said they're written right over there and they will stay there. They will be there. I will not ask you to memorize these. Said that. Same thing's true for speed of light. I'm not going to ask you to memorize useless information. This is stuff that you can look up anywhere and you're going to be using a lot, but I want you to be able to use it, not be able to memorize it. As Bo learned on our field trip the other day. It's more about, I don't know if you were listening, probably not. One of the professors said that. In the original talk. Okay. What do you think? This guy right here is the weird guy, right? You see him? He's called lambda. That's how you pronounce it. It's a Greek letter. And it means the wavelength. All right, now having said all that, let me show you why they're related inversely. Why are these guys related inversely? Yeah. This is a pretty obvious mathematical, relationship, because you see all the time. We saw it with density and mass and volume. If I take, watch what happens to the denominator in each of these cases. As I increase the size of the denominator, what happens to the size of the fraction? Everybody agree it's a smaller fraction? 1/20th is a smaller fraction than 1/2. So as the denominator increases, the size of the fraction decreases. So this guy's getting bigger, this guy's getting smaller. Everybody agree? Same basic idea. As you saw with the picture we saw a little while ago. The guys with really long wavelengths, okay, there were things on this end like radio waves and microwaves are hitting your body right now, doesn't really matter. Okay, guys with really short wavelengths, X-rays, gamma rays, I do care about them. They have a lot of energy, okay, because they have a very small, the smaller this wavelength is, the larger the energy change. Okay, now, let's use this equation at this point. Now, I've done my best to explain at least a little bit in the beginning here, each of these things, and what electrons look like. Now, does everybody understand what electrons are? No. Copy this question down. I don't think so. And we're going to do, for the next 2 days, besides today, we're going to do more and more stuff. We're going to see what happens to electrons when we excite them. We're going to talk more and more about what's going on with them. But for right now, I want you to be able to see if you can do a simple calculation with how our energy and wavelength is related, how the two are related to each other. And the reason I'm doing it, well, there's a lot of reasons, but one thing you'll notice when I do this is something similar to what I showed you when I first taught you how to do any problems. We're going to do them the same way, the same method. Remember the metric conversions? They came in handy in the following chapter when we were doing atomic conversions between moles and grams and atoms. Well, sure enough, when I taught you a very simple problem like D equals M over V, I told you to do it the exact same way I want you to do this. What did I say to write down first for the density problems? The given information. Remember? So let's do that. The given information, delta E equals H, C, and lambda. Those are the 4 possibilities, the 4 variables, I should say, I have in this problem. Read the question. This is the first step. If this said calculate the density and it gave you a mass and a volume, you know what to do. This is saying calculate the energy. What am I going to write down? What is the energy in this case? What do you think? Jared?
The question mark.
Exactly. Glad he didn't say 5.59. Some people just look for the first number. No, it says calculate the energy, right? So, good enough. What's H in this problem here? Barb? What's H? Let me give you a hint.
Question mark.
No, we can't have two question marks in the same problem. Let me give you a hint. It's one of those things we don't have to memorize.
Oh, it's
6.63 times 10 to the negative 34th joule seconds. See it? Right? Okay, what's C in this problem here? What's C? Maddie? 2.998 times 10 to the 8th meters per second. Good. And what's lambda in this problem here? Josh?
5.59 times 10 to the negative 7 meters.
Correct. All right. Now, the reason you do this way is so you can check your numbers, make sure everything's good, check your units, I should say. My units are okay. I don't have anybody that's measuring the same thing in different units, so I'm good. Next thing I'm going to do is what? What will I do next?
Write down the formula.
Right, write down the correct equation. Now, the correct equation, all right, is the only equation we've gotten so far. Delta E equals HC over lambda. Okay? I plug my numbers in, and I'm ready to go. I'm good to go. So delta E equals H, which is 6.63 times 10 to the negative 34th joule seconds times, and I'm abbreviating a little bit to fit on the board here because these are big numbers, 2.998 times 10 to the 8th meters per second over the wavelength, which is 5.59 times 10 to the negative 7th meters. Now, a lot of other stuff that I've given you, a lot of other things I've told you, you're using in this problem. Not only the method of doing this, but the algebra, we haven't had to use any yet, and significant figures and units. All of this stuff has to make sense at the end of the day. And plugging into my calculator exponents. Now, the other period we spent quite a while getting everybody to get the correct answer for this. Get your calculator out, plug this guy in. If you're plugging it in correctly to your calculator, we should all get the same answer. And I'm getting people who are not doing that yet because they're not. It should be 6.63 exponent button, not times 10 exponent button, that kind of stuff. Everybody plug it in and see what you get for your answer. I won't have time right now, because we don't have a whole lot of time here to actually, because I have another example to do to figure out who's doing what wrong if we don't get it right. But I will have an idea of whether you're doing it right or not. Tomorrow we can actually look at why. But did everybody get 3.56? Does that look good to you? All right, 3.56 times 10 to the what?
Negative 19.
Negative 19. Did everybody get that? And now here's the million-dollar question. What are my units? Well, watch what I do to figure that out. A lot of people want. Somebody asked me that working on the worksheet after having done these. Actually, did more in the other class because we have a couple period. I know what the units are because I kept them. And seconds will cancel with seconds. Meters will cancel with meters, and the only thing left is what? Joules. Now, does it make sense that an energy would be in joules? Absolutely. Those of you who are in physics know this. If you don't, if you're not in physics, joules is a unit of energy. You can use calories as well, but joules is the preferred unit of energy in physics class, at least. In my class, it's actually calories that count too. All right, let's do another example. And you know I'm going to change some stuff up on this one. Watch. Okay, copy that one down. You want to find the wavelength of light that has an energy of 3.5 to 10 to the negative 15th joules. Now, I said I'm going to change some stuff up, but it doesn't mean I'm going to change how I do the problem. I'm going to do it exactly the same way. Delta E equals HC and lambda. This last time, delta E was my unknown. What is delta E this time? Is it the unknown again?
No.
No. Emily, what's delta E?
Me, Emily?
Yeah.
Delta E, oh boy. It's going to be 3.5 times 10 to the negative 15 joules.
Correct. All right. And even if it didn't say that was the energy, you would know it because of the units being joules. Zach, what about the H? What's H?
6.63 times 10 to the negative 34 joule seconds.
Correct. Let's take C. What's the speed of light here, Emily?
2.998 times 10 to the negative 30 per second.
All right. And finally, the wavelength. Karen, what's the wavelength?
Unknown.
The unknown. Okay. Everybody good with that? Because it asks find the wavelength. Good. All right. Let's do the next step. What's my equation for this guy, Nikki? Delta E. Keep going. That thing's called lambda, right? Okay. Now, this time, I don't have him set up the way I want him. And I want you to rearrange him. I want you to show me a rearrange. I'm going to ask you right now, what will I have to do? To do this in steps, what will I have to do to both sides to rearrange it and get lambda by himself? Get an answer in your head. What will I have to do to both sides to get lambda by himself? First thing I'll have to do, Karen, what do you think?
By each side by
Multiply each side by what?
lambda.
Right, by lambda. What that does is not finish the job for you, but it gets lambda out of the denominator. Now I've got lambda delta E equals HC. Everybody see that? Now I can solve for lambda, because what will I do to both sides this time? What will I do to both sides this time? L.
You divide by delta E.
I'll divide by delta E. Delta E cancels, and I get lambda equals HC over delta E. Everybody good with that? And once again, I got to plug all my numbers in and make sure I can do the calculation correctly, cancel out the units, and keep significant figures. So lambda equals 6.63 times 10 to the negative 34 joule seconds. C is 2.998 times 10 to the 8th meters per second. And delta E is 3.5 times 10 to the negative 15 joules. Once again, plug that guy in. This is the one where more people have trouble on their calculators, I think.
There should just be a button that's like H, and it just plugs it in. Don't you think?
There probably are, and you could plug that. Actually, there's a way to do that. You could make on your graphing calculators, the ones that have memories, you could actually plug that in, and so you could just hit that button. You could use it as a memory function. Memory 1, memory 2, memory 3. You could make that an actual constant. Speed of light may even exist on some of them like that if it's a scientific calculator. So there is a way to do that.
Yeah, that's a lot of work, but I mean, it would pay off in the end.
Well, we aren't going to be doing these forever. What did we all get, hopefully? And round it to the right number of significant figures.
5.7 times 10 to the negative 11 meter.
Let's see. Joules cancel. Seconds cancel. You get meters. Does it make sense that a wavelength would be in meters?
Yeah.
Yeah, absolutely. And that's exactly what happens. Now, we're out of time. Obviously, we have 2 minutes left. You can copy that homework down, and you can start working on that. But you'll have, I'm telling you right now, I'm not going to check it tomorrow. You will have time to work on it.